Okay, perfect. So first of all, I would like to thank the organizers for this meeting and for the opportunity of being here to present a work that I've been done and will appear soon in the archives. So this concerns the Gravastar solutions of a particular class of modified theories of gravity called FOFRL gravity. So the outline of this presentation will be, so firstly, I will explain briefly what are gravastars, as they are gravitational condensate stars. Then I move forward in order to introduce the question why we need to seek beyond general relativity. And one of the main examples of theories that are being studied in the literature has an alternative to Einstein's theory, and then I will present the some of the results of the gravastar solutions of these kind of theories to end with some conclusions. Okay, so gravastar solutions. The idea came precisely when people were trying to understand black holes. In particular, the problem of event horizons in general relativity and their inconsistency with the definition of a universal time, which is needed for a Schrodinger's equation. So the idea of trying to get general relativity compatible with quantum mechanics, you see these regions where the gravity has a strong regime are also regimes where quantum gravity, whatever this kind of theory is, should appear and should have some implications. Therefore, the inconsistency of a event horizon with the definition of universal time, which is needed for instance, the Schrödinger equation, was a huge problem. In particular, a solution was advanced in the literature, namely by Chaplin et al. So, in their reasoning, the idea was that space-time itself has undergone a continuous phase transition to a de Sitter-like phase. So, as gravitational collapse occurred, this space-time undergone a continuous phase transition, and therefore there is no singularity happening. Instead, there was a region of a de Sitter-like phase. This idea was immediately captured by Moser and Motola in what is commonly known as gravastars, which are in fact a compact astrophysical object which is intended to be an alternative to a black hole. So in this, similarly to the reasoning of a quantum black holes by Chaplin et al., Moser and Motola tried to understand a different stage of a stellar object at their final life stage. So during collapse, the star undergoes a phase transition into a de Sitter region with a real physical boundary. So the event horizon is no longer a not physical boundary, but it becomes, in the gravastar scenario, a physical boundary. So the gravastar is composed of three regions in what concerns to space-time. So there's the interior, which is a de Sitter condensate. There's a shell, which covers the interior, and there's the exterior region. So an observer in the universe, far from the source, will regard the gravastar as a Schwarzschild solution. So if you look at, this is an interesting picture. If you Google it for a gravastar, the main pictures that we will have is this kind of alien-like device. So, but in fact, if you search thoroughly, you will find that a gravastar can be pictured in this form. So you have three main regions, namely the interior one, that I told you, with a positive cosmological constant. We have a shell, which is made of ultra-relativistic plasma, and you will have the exterior vacuum. So this is a non-rotating solution of the Einstein field equations, for instance, okay? So the line element can be put forward in this form. So it has a spherical symmetry, and it has two unknown functions which will only depend on the radial coordinate. So the idea is to find these solutions of this line element. So the interior, let us call the region, the shell region with a R1, the inner part of the shell. So the interior can be characterized from 0 to R1. And this region is a de Sitter solution. Therefore, the pressure is equal to minus the energy density. In general relativity, the energy momentum tensor is 0. The divergence of the energy momentum tensor, is 0. Therefore, the energy density, rho, is a constant. And we find that F and H are related to each other through an integration constant and can be written in this form. Okay, so this is precisely a de Sitter solution. In the exterior region, where there is no pressure or energy density, therefore, this solution is simply a Schwarzschild-like solution. But the shell is a different situation. So the shell can be characterized by the region lying between R1 and R2. And in this region, composed by ultra-relativistic plasma, the pressure is equal to the energy density. So it is useful to introduce this quantity W here, which is proportional essentially to the R squared times the energy density. Therefore, the field equations can be recast in this form. So a solution can be found. Nevertheless, this yields non-trivial way to grasp this the full solution. Therefore, Moser and Motola tried to introduce the thin shell approximation, so to have a region where this H is very small. And at the same time f of r too. So they are small but non-vanishing. So the idea is really we do not have an event horizon. And in fact, we can find these solutions. And in the entropy, for instance, can be computed is very small in comparison to the Bekenstein-Hawking entropy. Okay, so this is the idea of a gravastar. So general relativity, as you know, can be cast through the Einstein-Hilbert action here. And if we vary this action relatively to the metric, we find the Einstein field equations. And of course, from this, it's obvious, it's immediate to understand the implications of curvature and the energy momentum tensor. Namely that space-time tells matter how to move, whilst matter tells space-time how to curve. So, despite general relativity being a wonderful gravity theory, and we know that it's compatible with solar system constraints, it predicted the black hole shadow that we now have a first picture, or even the prediction of gravitational waves, or some more practical implications, namely the use of a GPS, for instance, so to really has implications for daily lives in everyone, and we know that it works perfectly fine. There is some conundrums to be dealt with. Namely, it lacks a fully consistent quantum version. It presents singularities. At large scales, in order to account for the data, we need to introduce two dark components, namely dark matter and dark energy. And it also has the cosmological constant problem. So you see, at large scales, we have the problem of extra mass in which is not directly observed in galaxies, in particular galactic rotation curves. We also have the bullet cluster, which exhibits two distinct regions, one constituted by gas and the other one which is composed mainly of gravitational waves, gravitational effects observed from weak lensing, which is presumably due to the so-called dark matter. And there are many candidates to dark matter or to dark energy, and even if they interact with each other. But so far, no satisfactory answer was found, namely, no direct evidence of them was found. So no particle, no fluid was directly found. So there are some... Sorry?
You have 5 more minutes, Claudio.
Okay, yes, thank you very much. So, one particular way to extend general relativity is to introduce a general function in the action functional, namely f of RL. In particular, if you vary this action relative to the metric, we get a kind of generalized Einstein field equations, which are much more complicated. In particular, there is the second order term, second order operator here, which yields more difficult solutions in comparison to general relativity. And in particular, the energy momentum tensor is covariantly non-conserved anymore. And in particular, you see here, it explicitly depends on the matter Lagrangian density. So it lifts the degeneracy that occurred for perfect fluids in general relativity in the well-known work of Brown et al. So in particular, solutions of f of R L theories called Gravastars can be found. So we resort to a line element similar to the one proposed by or used by Mosur and Motola, and the interior solution can be found. So it yields a rather complicated dependence on these functions, which under the assumption of constant curvature, we can find a solution which is exactly a de Sitter solution and has which is regular of the center of the gravastar. So the singularity is avoided even in FRL theories, at least in the subset of solutions that can exhibit this kind of behavior. As for the exterior, you remember, we wanted to look into a Schwarzschild-like solution, and these can be found, in particular, in the exterior where the pressure and energy density vanish, so the FRL theories reduce to the well-known f of R theories, and this is the solution for f of R theories in the the Schwarzschild-like metric. Okay, the thin shell approximation yields a rather complicated solution. So combining the two equations that we had for general relativity in a more elaborated way, we find this solution that can be solved, yielding an exponential of a rather complicated functions. Remember that we can look into subsets, namely constant curvature, some particular combinations, or some physically motivated solutions which can mimic dark matter and dark energy and get specific solutions for this line element, okay, and for Gravastars. So to conclude, and that since I have perhaps 1 more minute, so Gravastars are alternative to black holes and can be stable or unstable according to properties on the shell. We cannot, for instance, the thin shell cannot has some Planck scales, cannot reach Planck scales, otherwise it will be unstable, for instance. So there are some conditions. And in alternative gravity theories, there are new physical phenomena which may be of interest. And these solutions are really, really highly non-trivial to be solved, although some special cases can be analyzed, namely constant curvature, simple dependencies, or even when we can embed lambda CDM paradigm in these kind of theories, for instance. So thank you very much for your attention, and I hope that you enjoyed these kind of solutions, the Gravastar solutions, which are nowadays very interesting, given a lot of data that we are getting from, for instance, LIGO Virgo collaboration, as we have seen from the previous talk. So please please feel free to ask any question that you want.
Thank you very much, Cláudio. Only a short question.
Mm-hmm.
Yes, Martin, please. So 2 questions, short, please.
So, what is L in your theory?
Well, is the matter Lagrangian density. So the matter Lagrangian density for matter fields. Okay, for instance, it could be a scalar field, it could be a fermionic field. You see, it's matter fields.
Right. Okay. Thank you. So it's as a basic question. As I understood, in general relativity, you need this vacuum interior solution, then this stiff matter shell, and then so you need like 2 extra matter components. In the modified gravity scenario, because of this extra scalar tensor degree of freedom, can you not have extra matter and just be pure gravity? Or you still need this stiff matter?
Yes, that's a very interesting question. In fact, you see, these kind of theories really introduce a generic coupling between geometry and matter. So we still have matter. But what you are asking is quite interesting. For instance, let's suppose that you had a alternative gravity theory which did not depend on the matter fields. You can by trying to get some solution of the metric field equations, you can introduce an effective energy momentum tensor, which could be identified with a perfect fluid, for instance. And these extra curvature terms can play the role of ultra-relativistic plasma, for instance. You see, in these kind of theories, you can. In particular, this solution, the f of r L, what we are looking into is that we have matter, but the extra terms can also play a role in that sense that you can get the global picture of a kind of ultra-relativistic plasma, but composed of curvature and real matter.
Okay, thank you very much, Cláudio. Thanks, Cláudio, again.
Thank you very much. And I will stop sharing for the next speaker. Thank you very much.